Hey everyone, welcome back. In this video, we are going to go over the formal definition of the derivatives and review derivative notation. So, first things first, this is the formal definition of the derivative here. Basically, what we are doing in this case is we are finding the general rule for the slope, meaning for any x value. The alternative definition of the derivative is here. And notice one key difference. This is f prime of a. So this is the one we're going to use when we're looking for slope at a specific point. Notice also both of these are taking the limit. So remember back to our Unit 2 review video where we discussed how limits tie into the definition of the derivative. So basically what we're doing is we're looking at the secant line and we're bringing these 2 points basically closer and closer together to estimate the slope at a specific point, or to get our instantaneous slope. So now let's go through an example together so we can kind of see these formulas applied and see why they matter. So starting out, let's go back to our classic quadratic, our x squared formula. If we were to apply the formal definition of the derivative here, let me scroll back up so you can see it. There we go. What would we be doing? Well, first thing you have to know how to do is you have to know how to do f of x plus h. So how do we do that? Well, if we know f of x equals x squared, I tell my students to think of anywhere there's an x as kind of like a placeholder. So I actually encourage them to put parentheses there. And then all you're going to do is you're going to replace, if you're doing f of x plus h, you're going to basically erase this, like imagine taking your pencil eraser and erasing it, and all you're doing is you're plugging this in there instead. So we would do x plus h squared. This, in case you need to review this topic, this is called a composite function, where you have a function inside of another function. Okay, so that's how they got this here. That is our f of x plus h. Now we're just subtracting f of x, which is just x squared. It's defined right there. And then it's just over h. So now, how do we actually take the limit of this? First thing we have to do is we have to simplify our numerator. So let's go ahead and FOIL this out. So if we have x plus h squared, that's x plus h times x plus h, which gives us x squared plus 2xh plus h squared. And then I'm going to just keep going with my formula. So minus x squared over h. And I just don't have, well, let me just squeeze it in there. The limit as h approaches 0. Okay, good. Now my x squared minus x squared is just 0. So I'm going to go ahead and cancel that out. Now, what do I notice here? Well, one thing I see is that in my numerator, I have an h in both terms. So my greatest common factor is h. So now the limit as h approaches 0, I'm going to rewrite this by factoring out my greatest common factor of h. I'm going to be left with 2x plus h over h. Notice how beautiful that is, right? Now I can cancel out these h's. Now what am I left with? Well, the limit as h approaches 0 of 2x plus h. Now I can just do direct substitution. If I directly substitute 0 in for h, what am I left with? I'm left with 2x. Now let's zoom out and talk about what this represents. Well, it represents the derivative of x squared. So basically, this function, I'm just going to write it as y prime for now, this can give us the slope of x squared at any x value. So anywhere along this curve like this, we can use 2x to get the slope. So let's just look at a really quick example. Let's say somewhere over here, let's just say the point -2, 4. If I want to find the slope at that point, all I have to do is do f prime of -2, and then 2 times -2 gives me -4. So at that point, my slope would be -4. So that's why it's useful. It gives us the general rule for slope anywhere along the curve. Now, let's take a look at the alternative definition of the derivative, which is where we can find the slope at a specific point. So now let's say we want to find the slope when we usually typically use a. I was going to say x, but let's use a when a equals 3. So now let me go back up so you can see the formula we're going to be using. Okay, so now we're going to be using this formula. So you'll see that's what we have going on here. Since our a is 3, this is just subbed in where everywhere there's an a, we've now written 3. Okay, so now let's go ahead and go through this. First things first, f of 3 is just going to be, if our function f is f of x equals x squared, we're just going to take 3, plug it in here, plug it in here. 3 squared is 9. So that's how we got to this part here. And of course, f of x is just x squared. So we literally just rewrote that. Now, what do we have to do? Well, we have to factor our numerator. This is a difference of squares, so we can factor that down into x minus 3 times x plus 3. Now we can go ahead and cancel out these terms, and then all that we're left with is the limit as x approaches 3 of x plus 3. Again, now we can just use direct substitution. Plugging in 3 there for x, we get 3 plus 3, which is 6. Okay, great. So what does this tell us? Again, this tells us that the slope of x squared when x equals 3, so at this point, let's call that 3 comma 9, the slope at that point would be, our m value is 6. And this is the value we would use, tying this back to our previous video. This is the slope we would use if we wanted to get the equation of the tangent line. All right, last thing, this will be super quick, is just a refresher on your notation. There are 3 common ways of seeing the derivative notated. You can see them all here. These all mean the same thing. So dy dx, f prime of x, or y prime all stand for the derivative, which again represents slope. All right, thanks for watching.